Okay, so last class we had discussed subspaces and some of its related results, right? Okay, so now we'll move on further, and we have also given some tutorial sheet, a second tutorial sheet also we had given. So based on your vector space and subspaces and some of its problems related to that, right? Last class we had given some exercises, and I hope that will be useful for you. Now we'll move on further. I will discuss further concepts on basic linear algebra. Okay. So using these two concepts, subspaces as well as this vector spaces, now we are going to move on to the further topic, which something is called a basis. We are going to discuss the basis and dimension of a vector space V. So if you want to discuss about the basis, you need two things. One is the linearly independent set. Suppose because we are going to talk about a set, that set is called a basis. We are going to talk about it should satisfy two things. One is that that set must be linearly independent set, and it should span the vector space V. Okay. We should also define what is the meaning of spanning. Okay, that is also we should define. So there are three equivalent definitions. Okay, so we can have this whatever definition we want, we can make use of that. Okay, so there are some equivalent definitions for subspace spanned by a a set is spanned by a subspace A. Okay, W of a vector space V. Okay, so this is what we had written in last class. Okay, so we are going to discuss two things. One is that these are the problems we are given. 1 minute.
Sir, your screen is not visible to us.
Okay, just a minute. But it has been shared already. Okay, so let me share it once again. Is it visible now?
Yes, sir.
Okay, fine. Okay, so last class we had written these things. So basis and dimension. So based on that, we are going to discuss about the dimension of two subspaces W1 and then W2, and then what will be the dimension of W1 plus W2. This will be the final conclusion in this chapter. That's what I told you in last class. Okay, so we'll say this is a definition. Subspace uh, spanned by a non-empty subset of S. Okay, the definition is okay. Let us call it this is the first definition. The subspace spanned by, let's say S, which is subset of V. Okay, so this is nothing but the set of a linear combination of vectors, the set of all possible linear combination of vectors in S. Okay, suppose I want to say W is a subspace. W is a subspace of a vector space V. Okay, W is a subspace, and I want to say that W is a subspace which is spanned by S. Okay, which is nothing but whatever vector I take in that can be expressed as linear combination of all those vectors in S. If so, then we say that as nothing but W is subspace which is spanned by a set S. Okay, so we'll understand this when we discuss some kind of some problems or something like that. So the other way of saying that, suppose I want to say yes. Okay, suppose I want to take some vector alpha. Alpha is in V, and then alpha can be expressed as something like this: summation over I. Okay, summation over I, alpha I into Ci. But each of this alpha I, here see, this is alpha and this is alpha I. Each of this alpha I, let's say alpha 1, alpha 2, let's say etc, alpha n, all these must be in S. Okay, so whatever vector you take, alpha is in V, so that can be expressed as a linear combination of all those vectors in okay, in S. So that is called a subspace spanned by S, or you can say that it is a spanning set. The other way of saying that it is a spanning set. Something you want to say S is nothing but a spanning set. Okay, S is having a element something like this. Let's say alpha 1, alpha 2, etc. alpha n. I want to say that S is nothing but a spanning set of a vector space V, of a vector space V. So whatever vector I take in this V, so alpha is in V, which implies that alpha can be expressed as C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n. So then one can say that it is a spanning set. But if you look at some different books, they use different concepts, different approach. Okay, for example, if you see this Hoffman and Kunz, he defines in a different way. But anyway, that reminds that the meaning of that subspace spanned by the set is that is same only. Okay, he says that if I want to say the subspace spanned by S is nothing but intersection of all subspaces which contains S. That's what he says. But anyway, that the definition remains same only. That you don't worry about that. Okay, so meaning of the subspace span basis, this is the meaning. Okay, so I whatever is the finite, whatever the set is there of a vector space V, whatever vector you take in that vector space, that can be expressed as linear combination of these vectors in that set. Okay, so then one can say that is subspace span by S. So we'll look at some problems. Okay, so I'll write some problems. First, let us write the definition of your Hoffman and Quince, and then we'll write the equivalent definitions of others also. Okay. So we'll write, let S be a set of vectors. Let S be a set of vectors. Let S be a set of vectors in V. The subspace you can call it as a W. Okay, the subspace spanned by S is defined to be the intersection of all subspaces of V, intersection of all subspaces of V which contains S. Okay, so that means if the intersection of all subspaces of V which has this S means that is the same thing that whatever vector you take, that can be expressed as all this linear combination of these possible vectors. Okay, so in simple way of saying that, suppose you take S. Okay, suppose you take S is, let's take a vectors alpha 1, alpha 2, etc. alpha n. So S is a finite set. Okay, then we call W the subspace, W the subspace spanned by the vectors alpha 1, alpha 2, etc. alpha n. Okay, so this is what one can say, that W is nothing but W is a subspace which is spanned by these vectors alpha 1, alpha 2, etc. alpha n. S is nothing but any non-empty subset of a vector space V. As I told you that we can even write as there are another way of writing it. There are another way of writing is Okay, so there are another way of writing is okay. Maybe we may say those things are results, so we can make use of those results also. Okay, so maybe the alternative results we can say are definitions. We can make use of this resistor for the subspace spanned by a vector space. The subspace spanned by the result says that that's the same thing. The subspace spanned by S of a vector space V is nothing but the set of all possible linear combinations of vectors in S is the set of all linear combination of vectors set of all linear combinations of vectors in S. Or you can say the set of all possible linear combination of the vectors in S. So sometimes it is defined as the spanning set is defined by it is denoted by okay, span of S. It is denoted by span of S. Okay, just you write the span of S. That is span of S in V. You can say okay. Okay, first let us give one simple example. Then once we discuss some more concepts, then we'll give some more examples with respect to matrix. Also, we'll give some examples. Okay. First, let us look at some simple examples. We'll give one counter example. We'll take let S is equal to, okay, U2 union L2 in 2 2 M22 means 2 by 2 matrix, 2 by 2 matrix with real entries. Okay, 2 by 2 matrices with real entries. So where U2 is nothing but the set of all 2 by 2, the set of 2 by 2 upper triangular matrices. Upper triangular matrices. L2 is equal to, am I audible to everyone?
Yes, sir.
Okay. So L2 is nothing but once again this is a lower triangular matrices. Okay. So this is a set of 2 by 2, lower triangular matrices. Lower triangular matrices. Now we'll just see that what is the span of S now. What is the span of S? Okay. So the span of S is nothing but the complete the M 2 by 2 matrices. Okay, set of all 2 by 2 matrices. Why? Because if you take any matrix, okay, because every 2 by 2 matrix can be expressed. Why? Because every 2 by 2 matrix in okay, 2 by 2 matrices, okay, because we are taking this is nothing but U2 union of L2 because it is a subset of 2 by 2 only, set of all 2 by 2 matrices. Because U2 we are taking an upper triangular matrices, this is a subset of all 2 by 2 matrices in the form A, B, C, D. And similarly, this is also subset. So therefore, you can say that every matrix in M22 can be expressed as a linear combination of okay, upper and lower triangular matrices. Upper and lower triangular matrices. Let us look at this. See, so we have this A, B, C, D. General A, B, C, D. This is of the form set of all 2 by 2 matrices, right? In M22. Now, if you want to say something is called a spanning set, now this should be expressed as linear combination of the vectors in L2 and U2. Okay, linear combination of the vectors in S. So now this is very straightforward because I can just clearly see that A, B, C, D can be expressed as, okay, so I can just say that A, if I take out, this is 1 0 0 0 I can do, and B, if I take out, this is 0 1 0 0 I can do, and then plus C I can take out, this is 0 0 1 0 I can do, and plus D, if I take out, this is 0 0 0 1. Okay, so this is very clear that hello, யாரு? இல்ல இல்ல, ஒரு நிமிஷம் நான் கால் பண்றேன், இருங்க, கிளாஸ் போயிட்டு இருக்கு. Okay, so we have A 1000 plus B 0100 plus C 0010 plus D 0001. So I could clearly see that these are the things. Hello, am I audible?
Yes, sir.
Okay, so now this is nothing but what? This is an lower triangular matrices and then upper triangular matrices. Similarly, we have a lower triangular and upper triangular. So you can see that these all this thing, okay, all these matrices will be in S only. Yes, because these are the matrices of your lower triangular and upper triangular matrices. Okay, so 0010 and then 0001 are all in S. So now this is one of the simplest example I could give you, that if I take anything, vector space V is nothing but M of 2 comma 2 and S is nothing but a subset of this, and then the spanning S is called a spanning set. Why? Because whatever vector I take, means the general vector I took A, B, C, D, that is expressed as linear combination of all those vectors in S. Because 1 0 0 comma 0 and then 0 1 0 0, these are all an upper triangular and lower triangular matrices which are all in S. So therefore, any vectors in V can be expressed as linear combination of vectors in S. So which implies that S is nothing but a spanning set. So S is a spanning set. So we'll say S is nothing but a spanning set. Okay, so now we'll define further, which is something is called, as I told you earlier, basis. Now we are going to define basis. Okay. So basis, once again, it should satisfy two things. It should have a two conditions or two properties, you would say. One thing is that first of all, whatever subset you are going to say as a basis, first of all that subset must be linearly independent. Okay, that subset must be linearly independent, and then that subset should be a spanning set. Whatever set you take, that should be a spanning set. Okay, so this you keep it in mind. So if I want to say something is a basis, okay, let us say that if I take a vector, okay, if I take a set something is like, let's say alpha 1, alpha 2, etc., alpha n. So this is, I'm taking this as an S. This is a subset of a vector space V. Now I want to say this S is a basis. Now I want to say this S is nothing but a basis. Okay, so if you want to say this is nothing but a basis, there are two things as I told you. These vectors are linearly independent vectors. So S equal to alpha 1, alpha 2, etc. alpha n are linearly independent vector, and this set must be a spanning set. So linearly independent vector we know. Linearly independent means we know, right? And it's a spanning set means again you have to take something in this, and that can be expressed as linear combination of all these vector in this. If it satisfies these two conditions, such a set is called basis. So we'll say definition, we'll define two definition precisely, of course the same thing only but different way we are going to define. Definition 1, let V be a vector space. Let V be a vector space. A basis for V, a basis for V is a linearly independent set of vectors. Let V be a vector space. A basis for V is a linearly independent set of vectors in V which spans the space V. Which spans the space V. That's something but a spanning set. Okay. So the other way saying that we'll write in a precise manner as I told you like this. This alpha 1 and alpha 2 will consider. Suppose you take a set. Okay, alpha 1 alpha 2 set of vectors. A set of vectors is the basis of V is the basis of V if it has the following properties. It has the following properties. First thing is that S is a linearly independent set. Okay. S is a linearly independent set. S is linearly independent. The second thing, S spans V. Or you can say S is a spanning set. Okay. So S must be a spanning set and then S is linearly independent. If these two things are there, then you can say that it is a basis. There is one more definition also one can define. If you because spanning set means we know what is the meaning of spanning. We know if this okay. Let me just precisely. I'll just mention it. I don't write as a definition. The spanning set means what? Suppose I take a vector alpha is in V. Alpha is in V. Alpha is equal to, suppose I write summation over I Ci times alpha I. Okay, this is called a spanning set. So for every vector can be expressed as linear combination of these vectors. If this expression is unique linear combination exists, then you can conclude that if this expression is uniquely is written as a linear combination of these basis vectors, then one can say it is once again it is a basis of that. Okay, so we don't need to get into that because we'll mostly will focus on these two things only. Will because we know the concepts of linear independent, one can easily verify that that is a linear independent set, and then you can see that it is a spanning set or not. So we can have okay, one simple example I just want to give. One is nothing but the set of all standard basis. Okay, the standard basis, the last class also we have discussed. We took three vectors: 1 0 0, 0 1 0, and then 0 0 1, and we have proved that these vectors are linearly independent. Now I'm going to take those vectors in Fn. Okay, or in Fn means in terms of Rn, set of all real numbers with okay, with n tuples, set of all n tuples we are going to take. So one counter example we can give: standard basis in Rn. Standard basis in Rn. So we consider the vectors. Let us say it is E1. E1 is 1 0 etc 0, and then E2s will take 0 1 0 etc 0, etc. En we take 0 0 etc 1. We'll take these vectors. Okay, E1 we take as 1 0 0 0, and then E2 we take as 0 1 0 0, and then etc. En can be taken as 0 0, and then last entry would be 1. And of course it is very clear that this is a linearly independent vectors. Okay, because we can see that the set E1, E2 etc. En are linearly independent. We have seen because C1 E1 plus C2 E2 plus etc. Cn En, if I take this as 0, so C1 times, so that is 1 0 0 etc 0, plus C2 times 0 1 etc 0, plus etc plus Cn times 0 0 etc 1 equal 0, or you can write 0 0 etc 0. So which implies that one can clearly see that C1 comma C2 comma etc Cn is nothing but 0 comma 0 comma etc 0. So therefore, which implies that C1 equal to 0, C2 equal to 0, etc. Cn equal to 0. So therefore, the vectors are linearly independent is okay, obvious. So therefore, the vectors E1, E2, etc. En are linearly independent. Now, what we want to prove that we want to prove that this set is a spanning set. We want to prove that. Next, we want to show that. Next, we want to show that this set E1, E2, En are spanning set. Spanning set. Okay. So next, we want to prove that it is a spanning set. So okay, spanning set means what? We have to take something, some vectors. You take that some vector in that vector space V, which is expressed as linear combination of these vectors E1 to En. Okay. Suppose we take a vectors. So what is V? What is V here? V is nothing but Rn. Rn. Okay, so now we take a vectors. Let us take a vectors. Let A, let's say A1, A2, etc. An. Set of n tuples only we have to take. This is in V. Now, because I want to show it is a basis. I want to show it is a basis. Now I should show that this can be expressed as linear combination of these vectors. Now A1, A2, A3. Okay, there is a. We'll give some notation for that instead of writing these things. Am I audible to everyone?
Yes, sir.
Okay. So we'll give some notation. Let us give this. This is nothing but U. Okay. We'll give this set as U. U is equal to A1, A2, etc. An. Now I have to see that U. U is nothing but okay. U I'm writing. Now A1 times 1 0 etc 0. Now I'm just trying to check. Okay. A2 times 0 1 etc 0 plus etc plus An times 0 0 etc 1. So what is it? This is nothing but A1, and then it is very obvious because a1 and the rest of the values are 0, and similarly 0 comma a2 rest of the values are 0. So now this is a1 e1, this is obvious, plus a2 e2 plus etc plus A n. So therefore S is a spanning set. Now what we are given is that, okay, so we are given a vector a1 a2 etc an in V, and then I'm able to write that a1 a2 etc an as a linear combination of the vectors, okay, in the set S. S is nothing but e1 e2 etc en. So therefore we can say that, therefore this set e1 e2 etc en is a basis, is a basis for, which is called a standard basis for R. Okay, so using these concepts, let's have this result. You can say it is a theorem. So we have a basis and then we have a spanning set, right? Okay. So we'll take let V be a vector space. Let V be a vector space. Let V be a vector space which is spanned by. Let V be a vector space which is spanned by a finite set of vectors, which is spanned by a finite set of vectors. Let's say beta 1, beta 2, etc beta m. Okay, so which is spanned by beta 1 beta 2 etc beta m. Then any independent set of vectors in V, then any independent set of vectors in V is finite,
This what sir.
is finite and contains no more than m elements. So see what is given, we'll see that. Okay, V is a vector space, and then it is given that V is spanned by a set of vectors beta 1 beta 2 etc beta m. So what is the meaning of that? If you take any vectors in V which can be expressed as linear combination of these vectors beta 1 to beta m. So if it is so,
Ơi,
Okay, so we be a vector space which is spanned by a finite set of vectors, and then we have to show that any linearly independent set of vectors in V is finite. Okay, and which contains no more than m elements. That is what we have to show. So the other way of saying that, if the set has more than m elements, okay, if we say that every subset S of V which contains more than m elements, which is nothing but that set must be linearly dependent. This is the way of showing. Let's say that you are showing in terms of contradiction way, or you can say that in terms of instead of showing it is a linear independent set which has only m elements, you take more than m elements and you show that that set will have a linearly dependent. That is another way of showing that, because there are many ways to prove. Okay, in mathematics, one, if you want to prove something, you can use any approach. You can go for induction method, or you can go for whatever hypothesis given, you can directly make use of that, or you can prove even by contradiction approach also, or you can go for proving in the reverse way also. So there are many approaches for this theorem. Especially for this theorem has this approach. So what we are going to do, that we take more than m elements and we'll prove that this set is a linearly dependent set. Okay, that's it. The proof is very simple. So we have, okay, so we'll take that S is nothing but, we'll take S is a subset of V. Okay, we'll take that. So it is sufficient to prove that. We'll write that. It is sufficient to prove that. It is sufficient to prove that S is a subset of V. S is a subset of V which contains more than m elements. Which contains more than m elements. More than m elements is linearly independent, or more than m vectors, you can say. Okay, is linearly dependent. Is linearly dependent. So we are going to make use of the known result already. Okay, so we'll take S is nothing but, we have taken S is nothing but having a more than m elements. Okay, so we'll take that. Let us having S is set of vectors. Let's say alpha 1, alpha 2, etc. alpha n. Okay, where n is greater than m. With this condition we have taken. Okay, so we are taking more than m elements, so that is m is somewhere in between there. So n is greater than m. And what is given is that your beta 1 to beta m, etc. beta m spans the vector space V. So we'll make use of that concept also, since beta 1, beta 2, etc. beta m spans V. Spans V. What is the meaning? There exists a scalars. Let's have this aij. Okay, so instead of alpha, this one we'll take aij, because I'm going to use some concepts of matrix. So we'll just write aij. That is nothing but a vectors. Okay, aij. Okay, so now I have to write a linear combination of the vectors in this. Okay, so now we'll write there is aij in f. Okay, that means it is a scalars, such that alpha j can be expressed as, okay, alpha j can be expressed as summation over I runs from 1 to m. Okay, aij into beta I. See, because this is a spanning set. Okay, beta 1 to beta m is a spanning set. Span is V. So alpha j I'm taking as in V. That is possible because S is nothing but a subset of vector space V. So therefore alpha j should be expressed as summation over I is equal to 1 to m aij into beta I. This till m only, because the vectors are till m only. Beta 1, beta 2 to beta m only. It's not beta n. But then if I consider for any scalars, okay, this is another observation. For any scalar, for any scalars x1, x2, etc. xn we have, we'll take this combination. Okay, x1 into alpha 1 plus x2 into alpha 2 plus etc. xn into alpha n. What I want to show that this set is linearly dependent set, right? Alpha 1 to alpha n is a linearly dependent set. For that I have to first consider the linear combination. Okay, and then I have to prove that these each x's are 0 by using the concepts which is there here. Now what I can write, this is nothing but, now I can write summation over, okay, j equal to 1 to n, I can write xj into alpha j. See, I'm just writing this is x1 alpha 1, x2 alpha 2, etc. xn alpha n is nothing but what? Summation j equal to 1 to n, xj into alpha j. Since n is, n is greater than m, and then I can make use of alpha j by definition. Alpha j is nothing but summation over I equal to m 1 to m aij into beta I. So now I can make use of that. So this is nothing but summation over j xj into, in place of alpha j, summation over I, okay, I runs from 1 to m, j runs from 1 to n, alpha j is nothing but aij into beta I. Okay, so now these summations and the vectors are all can be interchanged, so this can be expressed as summation over, okay, I is equal to 1 to m, and then summation over j equal to 1 to n. I'm just writing scalars separately and then vectors separately. Okay, this beta is a vector, xj is scalar, aij is scalar. So these two are scalars now. Okay, these two are scalar and this is a vector. Now, by the matrix concept, we know one concept from the matrix. So, if n is greater than m, okay, n is greater than m, since, okay, since n is greater than m, since n is greater than m, there exists a scalars x1, x2, etc., xn, okay, scalars, not all of them are 0, not all are 0, such that this is true. Summation over j, so 1 less than or equal to I less than or equal to m. So, this is true. This is the results from matrix. Okay, this is one result is from matrix. If you choose something like this, there are aij into xj, j runs from 1 to n, but I runs from 1 to m. So if this is true, n is greater than m, so this relation will be always 0. Summation over j, xj, aij will be 0, but not all of these vectors are 0. Okay, not all of these vectors are 0, which implies that what? So by the previous expression, so you have x1 alpha 1 plus etc. xn alpha n equal to 0, but not all xi's are 0. But not all xi are 0. Xi's are 0. So which implies that if all these, at least some of the xi's are not equal to 0, so you can say that alpha 1 to alpha n, etc. alpha 1, alpha 2, etc. alpha n are linearly independent set. Sorry, linearly dependent set. So if you consider more than m vectors, so that will give us linearly a dependent set only instead of independent. So this is implies that, so therefore this implies that if you take any linear independent set which doesn't have more than m elements. So using these concepts, there is something is called we can reduce this corollary. Corollary means we are reducing some results from the previous result by the theorem. Okay, by the theorem we are reducing some results which can be proved shortly. That is the meaning of this corollary. Okay, if V is a finite dimensional vector space, if V is a finite dimensional vector space, finite dimensional vector space, then any two bases of V, any two bases of V, any two bases of V have the same number of elements. Okay, V is finite dimension means here we are not talking about the dimension. Okay, real line R1, R2, R3, etc. Rn. Here the finite dimension means it is purely connected to your basis. So V is finite dimension means it has a finite basis. Okay, V is a finite dimension vector space means that vector space will have a finite basis. So that means V must be something like this. Let's say you have okay, let's say you have alpha 1, alpha 2 to alpha n. It's a finite dimension. So then we say that it has a finite basis. Okay, so this corollary actually leads to us define what is the meaning of dimension of a vector space V. We know the dimension of a real line. Okay, we have R1, we have R2, we have R3, etc. That is different. But whenever we say V is a dimension of n, that means it has n element, it has n vectors. V is a dimension as 3, that means it should be first of all a basis. That basis contains the number of elements, that it shows the number of elements, that is called, which is called a dimension of a vector space. Okay, so that is how we are going to define the dimension. So what is this corollary says? Just read this corollary carefully. So V is a finite dimension, that is okay. You take any two bases of V. Suppose I take, okay, V is nothing but, that's what it says. V is nothing but a finite dimension. So therefore there are basis is finite. Let's say this is V, and then you take two, okay, two set. We'll say S1 and then S2. S1 and S2 is in V. We take these two set. Okay, so S1 and S2 you take, and those two are bases. You take those two bases. The corollary says that these two bases will have the same number of elements. Okay, suppose I take these two are subset, these two are subset of vector space V. Suppose you take that three vectors. S1 is nothing but you take alpha 1, alpha 2, alpha 3. That is the meaning of this. And then S2 also you take alpha 4, alpha 5, alpha 6. So these two bases will have the same number of elements, means the number will be 3, 1, 2, 3 here, and then here also you have 1, 2, 3. So therefore, the S1 and S2 will have the same number of elements if V is finite dimensional vector space. So one can ask now, sir, is there something is called an infinite dimensional? Yes, infinite dimensional vector spaces exist. So, but then we are not going to focus on infinite dimensional vector space, because infinite dimensional vector spaces are one of the examples of infinite dimensional vector space is nothing but Hilbert space, and one more thing is called Banach space. These two spaces are called infinite dimensional vector space. Okay, but that is out of subject. So Hilbert space and Banach space, these two leads a complete subject which is called functional analysis in mathematics. So we don't focus on this. That requires a lot of analysis, and these two requires complete another 6 months or 1 year to learn these two subjects. Okay, so these two concepts to understand this number of elements. I will write this number. The number of elements of we. Suppose we have spoken a basis